So, okay, welcome to this course, that fundamentals of electrical engineering. So, before giving you introduction, just I would like to tell one or two words. That is, this course is mainly for the first year engineering student, or in fact all the first year engineering student can take this course, and this is a very basic course. Only at the beginning I am telling that in the introduction, that video, that 5 minutes video, there one thing I said only independent sources, but I found that dependent sources also, it is very simple thing. So, dependent sources also will be covered. So, these are the things, and we will start from the basic concepts, right, basic concepts, and from there we will your what you call, slowly and slowly we will move into much deeper understanding, and your first the DC part will be covered, and then with single phase, 3-phase AC circuit, everything will be covered by your, including resonance, maximum power transfer theorem, and your what you call that magnetic coupled circuits, and then whatever first year courses is there for your transformer, single phase transformer, equivalent circuit, and up to voltage regulation, then little bit of 3-phase induction machine up to your equivalent circuit, as well as first year course is concerned, and then the DC machine, right. So, this way let us start. First thing is that your basic concept, right. So, generally all branches of electrical engineering actually are based on two things, that is your electric circuit theory and electromagnetic theory. I mean, this is the your what you call that main two things. So, several branches in electrical engineering, like your power system, control system, electric machines, instrumentation, then electronics, then communication, all are based on your electric circuit theory, right. So, this course is mainly your what you call that your suitable for your what you call the first semester or your first year as an electrical engineering student. And so, we will start from your very basic thing. So, therefore, the basic electric circuit theory course is your important course for an electrical engineering student, and of course, an excellent starting point for a first semester student or first year student in electrical engineering education. Electrical engineering means it covers all the things like electrical, then your electronics, ECU call, then your instrumentation. So, everybody, I mean all the specialized in first year, they can take this course, right. And so, and basically if you think about electrical engineering, we are often interested actually in transferring energy from one point to another. This is common idea you have when you look at the circuit at household, and you might have seen somewhere that power generating station, right. But ultimate thing is that we often interested in transferring energy from one point to another, that is also you are transferring energy. So, to do this we require an interconnection of electrical devices, right. So, and such interconnection is known as an electric circuit. Like if I mark it by this this plane, we require an interconnection of electrical devices, and such interconnection is known as an electric circuit, right. And each component of the electric circuit is known as element. So, what we need actually, we require an interconnection of electrical devices, and interconnection it will be through wires only, conducting wires only, and such interconnection is known as the electric circuit, and each element of the electric circuit is known as your element. That means, each component of the electric circuit is known as an element, right. Therefore, an electric circuit is an interconnection of electrical elements. So, this is the your what you call, this is your the I mean requirement, your electrical elements, and electric circuit is an your what you call, therefore, electric is an interconnection of electrical elements. So, so just we will come to the figure 1. It shows a simple electric circuit, right. So, it consists of 4 basic elements. Look, just look at this circuit. It consists of 4 basic elements. One is voltage source. This is very very basic things we have started. So, this is a voltage source representing says battery. This symbol will come later. Battery symbol will come later. This is a switch, and this is a conducting material. If you close this, switch will be closed. If it is open, it is open. And this is actually conducting wire. There is a conductors representing wire, and this is the lamp, and this is the filament. Say it is made of tungsten, right. So, this is a simple circuit. So, a lamp connecting such a simple circuit has several applications such as your torch light or a searchlight etc. So, this is a simple electric circuit. Now, let us come to the voltage source representing a battery. So, basically what happened, electrical charge, that is electrons, say in bracket we are writing electrons, will flow through the circuit due to chemical forces in the battery, right, due to the chemical forces in the battery. Of course, little bit of your battery, regarding little bit of physics here. In physics you have studied the batteries, right. So, here we will not your what you call, here we will not cover to the chemical reaction another thing, but some whatever we have learned from there only we will talk about that. So, will flow through the circuit due to the chemical forces in the battery. The charge gains energy from chemicals in the battery and delivers energy to the lamp, right. So, this regarding charge I will come little bit later. So, the charge actually gains energy from the chemicals and in the battery and delivers energy to the lamp. Actually, from here actually energy is coming to the lamp, right. And the battery voltage is a measure of the energy gained by a unit of charge as it moves through the battery. Later we will see the your voltage and other things, but the battery voltage is a measure of the energy gained by a unit of charge as it moves through the battery. But of course, if the switch is closed, right. But one thing is that suppose this conductor wire, suppose it is a what you call the copper wires, and that plastic insulation will be there, right. And this is the tungsten wire actually is not a good your what you call a conductor as compared to the copper. We will come to that, right. But question is, the wires are made of copper conductor, I just told you, and are insulated from one another by electrical insulation coating the coating the wire, that you have seen. So, electrons actually readily move through the copper conductor, but not through the plastic insulation. So, this wire is there, but it is your plastic insulation, right. And a switch I told you, it will allow or disallow the current. If you close the switch, current will flow. If you just open it, then current will not flow. So, and the lamp actually I told you it contains a tungsten wire. It can withstand high temperature. So, tungsten is not as good as your electrical conductor or as copper, and the electrons actually experience collisions with the atoms of the tungsten, right, and that is the tungsten wires, because that is through the copper conductor that your what you call charge or electron is flowing, and it will make a your what you call collision with the atoms of the tungsten wire. So, therefore, resulting in heating of the tungsten, and we can say that tungsten wire has electrical resistance. So, thus energy is transferred by the chemical action in the battery to the electrons, right, and then to the tungsten where it appears as heat. So, the tungsten become hot enough so that light is emitted. So, I'll put a question to you that your that is your many questions on this thing when I will move so whatever that electrons flow, just let me go to this circuit. Just hold on. That actually electrons is flowing through this copper, and when it comes to that, it is collision actually with the atoms of the tungsten, and therefore it is causing heat. So, that means we can say that tungsten has an electrical resistance, right. And I will put a question here that you have seen that your that bulb 40 watt, 60 watt and 100 watts and so on. So, they have all the filament, tungsten filament, say. So, a question to you, what is the diameter of this tungsten filament, because if you see it, then you will find it looks like a coil, right. And what is that your diameter of this tungsten filament? This is a question to you. So, this is actually your what you call that how that we get that your bulb this thing, right. So, 40 watt that later we will see 40 watt, 60 watt or 100 watt, right. Therefore, the energy is transferred by the chemical action in the battery. The battery has a chemical action. So, that energy is transferred in the electrons and then to the tungsten where it appears as a heat. So, tungsten become hot enough so that light is emitted. So, this is a basic philosophy of your what you call that a simple circuit, a simple DC volt, a simple switch, wires, and your tungsten lamp, whatever you see in that your what you call 40, 60 or your 80 100 watt bulbs. So, now system of units, actually in all electrical engineer this thing we deal with several measurable quantities like voltage, your then current ampere, right, power, watt and so on. So, however, our measurement must be communicated in a standard language such that all engineering professionals can understand irrespective of the country where the measurement is conducted. Such an international measurement language is the International System Unit, that is we call in short SI units, right. It is International System Units, we call SI units, right. So, adopted by the General Conference on Weights and Measure, that was in 1960. So, we follow that your what you call that SI is SI unit, we call International System of Units, in short we call, other way we call is SI, right. So, basically in this international system there are 6 principal units, basically only 6 principal units, from which the units of all other physical quantities can be obtained, right. So, just I am giving you the 6 units. So, table 1.1 it shows the 6 principal units and their symbols. The SI units are used throughout the world, right. So, one major advantage of the SI unit is that it uses prefixes based on the power of 10 and to relate smaller and larger units to the basic units. So, table 1.2 shows SI prefixes and their symbols, we will come to that. First, these 6 basic SI units, right. So, this is the your 6 basic, one is luminous intensity candela, that is we call CD, right. Another is the thermodynamic temperature Kelvin, in short in your symbol is K. Another length meter, symbol is M. Another is mass kilogram, it is kg. Another is time, it is second, and electric current in ampere A. This is the 6 standard international or what you call SI units, from which other can be obtained. So, this is the 6 your basic SI units. So, it should be in your mind. And then your table 1.2, it is actually you will see that the SI prefixes. So, there are many, 1 or 2 I am making that, like if it is 10 to the power 18 it call exa, its symbol is capital E, you know. This is 10 to the power 15 we call peta, its capital is your what capital P we call. 10 to the power 12 we call tera, it is T. Then 10 to the power 9, right. So, it is giga, it is G. Then when come 10 to the power 6 it is mega, right, it is M, and so on. 10 to the power 3 is actually it is not coming to align to this, but 10 to the power 3 means kilo. So, accordingly numbering you can make it, right. It is K. So, this way your deca, deci, centi, milli, micro all, but last one is 10 to the power minus 18, it is called atto. In small a we call A, 10 to the power minus 15 it is called femto F, and 10 to the power minus 12 it is pico P, and so on. So, from 10 to the power 18, that 10 to the power plus 18 to 10 to the power minus 18, these are actually your what you call the SI prefixes. This is multiplier, this is prefix, and these are the symbols. So, first basic 6 SI units, and these are your what you call the SI prefixes. So, this we should know, right. Next is the charge and current. Now, the concept of electric charge is the underlying principle of explaining all electrical phenomena. The most basic quantity in an electric circuit is the electric charge. Here we will review some important characteristic of electric charge. Then we will come to the current. Actually, current is the rate of change of your what you call the charge flow. So, we will come to that. The first one is the charge is bipolar, meaning that electrical effects are absorbed in are described in terms of positive and negative charges, right. So, charge is bipolar. So, it means electrical effects are described in terms of positive and your negative charges. So, first thing. Second thing is, according to experimental observations, the only charges that occur in nature are integral multipliers of the electronic charge, that is E is equal to, this you know from your class 12 physics also, E is equal to minus 1.602 into 10 to the power minus 19 coulomb, right. So, this is your the only charges that occur in nature are integral multipliers of the electronic charge, that is this value. And third point is the electrical effects are attributed to both the separation of charge and your charges in motion. And the fourth point is the law of conservation of charge states that charge can neither be created nor destroyed, only transferred, right. So, it neither you can create nor you can destroy, only it can be transferred, right. Thus, the algebraic sum of the electric charges in a system does not change. So, the fourth one is very important, right. So, this should be in your mind. So, effects of electric charge can be experienced when we try to remove our woolen, I mean you might have seen also, remove our woolen sweater and have it stick to our body, or walk across a carpet and receive a shock. Other electrical charges, I mean if you, I mean when we remove your woolen sweater in winter, you can see that it is your sticking on our body, this is due to the electric charge. Or sometimes we get some kind of shock when you are walking, you receive a shock when you are walking on a carpet. Other thing is that you take a very small pieces of paper and keep it, and if you take a plastic and rub it on your head, and just after that you hold it on this piece of paper, you will find that all piece of papers are attracted towards your, what you call, towards that plastic, right. You can experience of your own. So, anyway, so therefore, charge is an electrical property of the atomic particles of which matter consists, measured in coulomb. So, charge unit of charge is a coulomb, and it is an electrical property of the atomic particles of which matter actually consists. So, measured in coulomb. Now, consider the flow of electric charges. So, actually this is actually, do not look at this, is actually page number, right. So, now consider the flow of electric, a unique feature of electric charge is that it can be transferred from one place to another place. That means it is mobile. That means charge can be transferred from one place to another. So, hence it is mobile. When it can be converted to another form of energy, right, and the motion of charge creates an electric your fluid, we call it is current. So, now little bit we have to see that when we know that a conducting wire consists of several atoms, right, and a battery is a source of electromagnetic force. So, conducting wire consists of several atoms and a battery is a source of electromotive force. When a conducting wire is connected to a battery, the very first example what we saw, that a voltage source, a switch, conducting wires and a tungsten lamp, right. The charges are compelled to move. So, as soon as a battery is there, a conducting wire is there. So, as soon as you connect the wire across the battery, so what will happen? Charges are compelled to move. Positive charges move in one direction and the negative charges move in the opposite direction, a very simple logic. This motion of charges create electric current. Now which direction of the charge we will consider the direction of the current. Convention is to take the current flow as the movement of the positive charges, that is opposite to the flow of negative charges as shown in next figure 1.2. So, if you look at this, suppose this is battery, this is shown little bit bigger way to show that your charge flowing. So, this is actually negative charge flowing, this is the negative terminal, this is the positive terminal. So, the charge will flow in the direction of the your what you call positive flow of charge. So, this way, so that is the from plus. So, this is the convention. So, this is the direction of the current, or in other way it is opposite to the flow of the negative charge, this is the flow of negative charge, it is moved, this is minus. So, it is moving in other way. So, this is actually convention. Therefore, if you look into that, if you look into that, the convention is, this is a convention is take the current flow or the movement of positive charges that is opposite to the flow of the negative charges as shown in figure, this is figure 1.2. So, the way the direction of the positive flow charge is the direction of the current, or the opposite to the negative flow of the charge. So, the electrical effects caused by charges in motion depend on the rate of charge flow. The rate of charge flow is known as the electric current. Suppose if Q is the charge, T is the time and I is the current. So, I actually is equal to dq by dt. So, mathematically the relationship between current and charge and time is dependent that I is equal to dq by dt. This is the equation 1.1, that I is the current in ampere, Q is the charge in coulombs and T the time in second. So, basically current is your what you call by is equal to dq by dt. So, you note that 1 ampere is equal to 1 coulomb per second. That means, if this side is 1 ampere, this side it has to be 1. So, this is coulomb, this is second. So, it will be 1 coulomb per second, right. Suppose if q, for example, suppose you take that data in such a fashion such that the dq is 5, dt is also 5. So, that way, so it will be your what you call that 1 coulomb per second, right. So, the charge transferred between the time t0 and t is obtained by integrating both sides of equation 1 we get. That means, suppose at initial time t is equal to t0 and your final time is t, then if you integrate this equation, if you make this equation, therefore, that q can be made that is equal to t0 to t I dt. That means, this one if you come, that your dq is equal to I into dt, therefore, q is equal to integral of t0 to t then I dt. So, that is equation we are writing, q is equal to t0 to t I dt, that means charge transferred, right, between time t0 and t. So, this is the equation, q is equal to t0 to t I dt. This is equation 1.2, right. So, that means equation 1 suggests that current need to be a constant valued function. That means, here from this equation 1 it suggests that currents actually need to be a constant valued function, right. So, constant valued function, as we will see later, there can be several types of current, that is your charge can vary with time in several ways. We will see both DC and AC. AC at the time we will see current is time varying, right, and for DC actually current is constant. So, it is not time varying, right. So, when a current is constant with time, right, we say that we have direct current, that is DC current. I will show you the diagram. Thus, a direct current is a current that remains constant with time. So, I mean it is your what you call it is your whatever may be the time, the current is constant. On the other hand, a current that varies with time and reversing direction periodically, that is plus minus say, right, is called the alternating current. This alternating current we will see for AC circuit, not now, but little bit of diagram and other things I will show you for the sake of your what we call understanding. So, thus an alternating current is a current that varies with time periodically, right. So, that means it will be plus minus. So, alternating current is used in our household, because all our household everything is a AC source, AC power, right. So, AC circuit we will see later, first DC then AC, to run the refrigerator, toaster, air conditioner and other electrical appliances. Whatever residence we get, these are all your AC power, AC voltage, AC current, right. So, but DC that current is constant. So, figure 1.3 actually shows the values of a DC current and a sinusoidal AC current. So, in this case this is understandable, this is sinusoidal, a little bit has portion has cut, but this is sinusoidal and this is figure 1.3. So, this is a DC current, this is current, this is time second, it is a constant. Suppose current DC current is the 3 ampere, it is constant, right, whereas this is actually aperiodic, this is periodically changing from plus to minus. So, this is AC current, this is a cosine function and this is your AC current, it is given I is equal to say cosine 2 pi your 2 pi t, just hold on, that this is the function I is equal to cos 2 pi t, right. So, this is AC current we will see later. So, and this is example of DC current. Now, figure 1.4, that means this one shows the other types of time varying current such as the triangular and square wave. This is also time varying current, this is a triangular function, this is current and this is also it is a rectangular one, this is also changing periodically. So, plus minus, this is also, this is triangular waveform, this is square waveform, this is also alternating current, right. So, now as we have seen earlier, the direction of current flow is conventionally taken as the direction of positive charge movement. I told you that current, when you take the battery symbol plus minus, from the plus the positive charge is flowing. So, that is why it is taken as the direction of the positive charge movement. So, based on this convention, a current of 4 ampere say may be represented your positively or negatively. This is shown in figure 5, where a lamp is connected in series with a battery. Look how it is. starting from this, we will try to understand everything. Then later stage, you will find things have become very simple to us. So, what we will do, just try to understand the basic flow, basic understanding. If this is clear, then you will find circuit theory, this your what you call the circuit part and other things are very simple. For example, this is a battery, but battery symbol and other things will come later. This is a battery, this is plus symbol, minus symbol, and this is your two terminals are marked 1 and 2, right, and this is your say tungsten lamp, this is a lamp, and when you take look 4 ampere current say is flowing, say 4 ampere current is flowing. So, it is 1 to 2, it is given 1 to 2 4 ampere, then what will be I 2 to 1? It will be just opposite, no, it will be minus 4, because this current actually moving like this. When you take this current is coming like this I 1 2, and but when you take reverse direction, that I 2 1, it will be minus 4 ampere. So, in this figure I 1 2 is 4 ampere, this means the current to the lamp with its reference direction pointing from 1 to 2. This is the reference direction 1 to 2, that means if you take 1 to 2 4, that means current is flowing 4 ampere 1 to 2 positive, right. But if you take other way, suppose if you take 2 to 1, that it will just negative sign, it will be minus 4 ampere if you take 2 to 1, just reversal of the your what you call the direction, because here we have taken I 1 2, here we have taken I 2 1. Therefore, your I 2 1 is the current with its reference directed from 2 to 1. Of course, I 1 2 and I 2 1 are the same in magnitude and opposite in sign. So, because they denote the same current, but with opposite direction. Thus, we have I 1 2 is equal to minus I 2 1 is equal to 4 ampere. The magnitude is same, but I 1 2 is 4 ampere, therefore, I 2 1 is equal to minus 4 ampere. So, this is equation 1.3. So, this part is very simple, but understandable. If you reverse, that means reference direction 1 to 2 means from 1 to 2 4 ampere. If you take this is reference direction 2 to 1, the sign will change, then I 2 1 should be minus 4 ampere. Therefore, I 1 2 is equal to minus I 2 1 is equal to 4 ampere. Current magnitude will remain same, only the sign part, right, other way. So, this is actually little bit understanding of the current. Next is the voltage. So, now current part is gone, now voltage. As explained in the previous section just now, to move the electron in a conductor in a particular direction, it requires some work or energy transfer, right. So, this work actually is done by external electromotive force EMF, typically represented by the battery as shown in figure 1.2, right. So, this is your figure 1.2. So, this is actually external electromotive force EMF, typically represented by the battery. Figure 1.2 will come. This EMF, now this figure 1.2 we have seen that your one voltage source, then your what you call tungsten filament lamp, right. This EMF is also known as potential difference, or we call sometimes voltage, right. Actually, whenever positive and negative charges are separated, energy is expanded. So, this EMF is also known as the potential difference and voltage. So, actually whenever positive and negative charges are separated, energy actually is expanded. So, voltage is the energy per unit charge created by the separation. Thus, the voltage say V 1 2 between 2 points 1 and 2 in an electric circuit is something like this. Suppose this is your actually 2 points, say we will come to that other thing. This is the 2 point, this is 1 and 2, and this is the voltage say V 1 2, and this is the lamp, right. Therefore, when you come here, thus the voltage V 1 2 between 2 points say 1 and 2 in an electric circuit is that energy or work needed to move a unit charge from 1 to 2. We express the ratio in differential form, that is V is equal to small v is equal to capital V 1 2 suffix is equal to dW upon dQ, where W is the energy in joules, Q is the charge in coulombs, and V 1 2 the voltage in volts. So, voltage actually that is your V 1 2 actually dW of dW by dQ. The W is the energy in joules and Q the charge in coulomb. So, in equation, so this is actually your equation 1.4. Therefore, equation 1.4, it is evident that 1 volt is equal to, if it is this side is 1 volt, it will be 1 joule per coulomb. So, that is why it is 1 joule per coulomb, or 1 joule is equal to your 1 Newton meter. So, 1 Newton meter per coulomb, but 1 joule per coulomb generally we use. So, thus voltage or potential difference is the energy required to move a unit charge through an element, right. Just I say, that is why I underline the voltage or potential difference is the energy required to move a unit charge through an element. Like figure, look at the figure. Figure 1.6 shows the voltage across a lamp connected between points 1 and 2. The plus and minus symbol signs are also given. So, this is the polarity, this is the 1 and this is 2, 1 is positive, 2 is negative. So, signs are used to represent reference direction of voltage polarity. So, the voltage V12 can be interpreted as your in two ways. First thing is this point you try to understand. First one is the point 1 is at a potential of V12 volts higher than point 2. Look at this diagram, right. This point is your at a potential of V12 higher than this your what you call that other point 2. So, that means point 1 is at a potential of V12 volts higher than point 2, or the potential at point 1 with respect to point 2 is V12, or the potential at point 1 with respect to point 2 is V12. Second one is easier to remember, right. So, this is the concept, the plus minus, right. So, in this case either point 1 is at a potential of V12 volts higher than point 2, or the potential at point 1 with respect to point 2 is V12, right. So, therefore, the logically it follows that V12 is equal to minus V21. That means, if you take say V, so for example say just for example say V12 is equal to just 1 minute say why is whiteboard? Okay, thank you. We'll be back again. Thank you.